and privilege to welcome Dr. Vint Cerf. He doesn't need any kind of introduction, but still I'll try an attempt to introduce him. So Dr. Vint Cerf is one of the fathers of Internet, and he's a co-creator of TCP/IP protocols, which most of the engineers in India, we have many engineers, sir. As you know, like we produce almost 1.4 million every year, and we all studied your TCP/IP protocol, sir. And it's a great honor to really meet you virtually today. Dr. Vincent is a recipient of Alan Turing Award, which is kind of like a, say, Oscar or award for this area. He has already won a Marconi Prize. He has received Presidential Medal Award for Freedom. Dr. Vincent Cerf has received so many awards, numerous awards. He has so many patents with him. While he was working with Defense Advanced Research Projects Agency, DARPA, he actually worked on TCP/IP protocol. He was one of the major proponent of making internet privatization. Without wasting much time, sir, I give this virtual stage to you.
Thank you very, very much for that kind introduction. And if anyone is curious about details, they can always look me up on Wikipedia. There's a fairly good summary there of my story. Well, today's discussion is about the desirable properties of a data sharing regime. And so what I wanted to discuss is the kinds of things that we need to consider as we think about sharing of data on a significant scale. One of the things that the World Wide Web and the Internet have introduced is the possibility of generating and distributing and sharing and getting access to a very significant amount of data. The question, of course, is what to do with it and what properties would we want this data sharing regime to have in order to make the data useful. So that's what I'd like to concentrate on for the next half hour or so. The first thing I would argue is that data isn't very helpful unless we actually understand what it means. And the typical way we do that is to associate metadata with the data. So that might include quite a wide range of important characteristics. What does the data represent? What are the international units that describe the data? I mean, if you have a collection of data that's just numbers, and you're not told its pressure per square inch, or its temperature in centigrade, or its some other unit, if you don't know what the units are, then the data is useless. And so having a common agreement about how to describe what the data is very important. And so I would incorporate that into a much longer list of metadata that we associate with the data. And of course, we want the descriptors to be widely understood on an international basis so that when we share data around the world, we can make sense of what that data means. But that implies some other desirable facts that we would like to have about the data. And one of them is, where did it come from? Another is, when was it collected? Another is, how were the instruments that collected the data calibrated? Now, this, I think, is a very important question, because if you collect data through some instrument or other, and you don't include, along with the data, any indications of how the instrument that was collecting the data was calibrated, then it may be impossible to figure out how to take that data and make it comparable or make it comparably shareable or commensurate with other data. And as I'm sure many of you will appreciate, science is often about accumulating data from a variety of different sources, a variety of different experiments, all of which are intended to illuminate our understanding of how things work. As many people will tell you, if you can't measure it, it's pretty hard to understand it. So having a clear understanding of the calibration of the instruments that were used to collect the data is another important piece of metadata that we might want to include. Another thing that we would want to know is what the provenance of the data is. You know, who generated that data? Where does it come from? That's important because we may need contextual information in order to make sense out of the data. For example, let's suppose that this is data associated with geological information. And we have rock samples and things like that. It might be very important to know the physical location where the data was collected, and maybe even in detail, where was it collected in terms of striation in the layers of the Earth, so that we have some idea of how old that information might be. Where does it sit in the time series of the evolution of the planet? And so that's another example of the importance of contextual information when we accumulate data. I hope you're getting the idea here that all of these metadata things may be as important as the data themselves. Otherwise, the data may not be usefully interpreted. There's another issue which arises, and it's largely in consequence of a lot of data being collected in digital form. And that is the question of preventing the data from being altered, or at least being able to detect that the data has been altered. And of course, as scientists, you might say, why would anybody do that? But it's amazing how people will discover various motivations for altering data in order to obtain a particular outcome. Of course, in the scientific community, we all consider that to be completely egregious and totally unacceptable. And yet, I think all of you will be well aware that from time to time, this does happen. So things like digital signatures can be helpful in sort of locking up data in such a way that if it is altered, it's detectable. And that is a technology which has evolved since the mid to late 1970s using public key cryptography as a way of locking information. You might still be able to change the data because it hasn't been, access to it hasn't been inhibited. But if you use digital signatures to compute an encrypted hash over the data, and somebody changes the data and you do the same computation, you could in fact detect that data has been altered because the party who made the alteration doesn't have the private key to re-sign the altered hash. So I think that it should be part of our discipline in data science to assure that the digital versions of data are protected from alteration, either deliberate or perhaps accidental alteration. Another thing that we should be very worried about is the preservation of data, particularly if it's in digital form. And I've spent a substantial amount of, I would say, the last 20 years or so pursuing digital preservation techniques. And I can tell you that the more you look into this, the more complicated it gets. So let me see if I can just illustrate some of what might be helpful here. One of the problems that we run into is that when we are processing information in digital form, we often end up creating fairly complex digital objects. I mean, think about a spreadsheet. That's a very complex object. It has data embedded in it. And it may very well be that the raw data is less useful than the data as it's presented inside of a spreadsheet, because the relationships among the various pieces of data might be more evident in the spreadsheet form. But let us imagine that you've accumulated data and it's in a particular format, it's encoded in a particular binary way, and perhaps it's sitting on a medium like magnetic tape. One of the biggest problems that NASA here in the US has had historically is maintaining data and its accessibility over long periods of time. if you think about the moon landings, which occurred starting in 1969, we have the problem that much of the data that was accumulated was digitized and put on magnetic tape, and then the magnetic tape deteriorated and we couldn't read it anymore. And so one of the problems we have is that the medium may not be long lasting, and the data has to be copied in some reliable way into new media. As time goes on, if you want to have access to data that might have been collected 100 years ago or 50 years ago or even 10 years ago. This problem arises in other media as well. Some of you, I'm sure, might remember a time when digital information was recorded on 5¼ floppy disks, which had the amazing 100,000 character capacity. And those were subsequently replaced by 3½ floppy disks. And those were replaced by CD-ROMs, and those were replaced by DVDs, and those have been replaced by other things like memory sticks and other high-density digital storage media, external disk drives, and all that sort of thing. And what I have discovered over time, as perhaps you have as well, is that even if the data is still present on the medium, whether it's the 5¼ floppy disk or a CD-ROM or something else, even if the data is still there and intact, it could be that you can't find a functioning device to read the data. And just as a kind of an illustration of this, this morning, by sheer happenstance, I was poking around in my records and I found a notebook of a visit I had made to Irian Jaya, which is now called West Irian, in 1993, which is some 27 years ago. And as I was flipping through the notebook, I discovered a Kodak CD-ROM of images that from photographs that I had taken in 1993. And it occurred to me that I might not be able to read that CD-ROM. I might be able to actually get some bits off of it. But one of the problems is that it was designed to operate with an IBM-based Microsoft operating system. And it had .exe software extensions for it. And at the moment, I only have Apple Macintoshes around the house. And so that CD-ROM is not useful because I can't load and run the software that would correctly interpret and render the photographs. So now I'm going to have to go find an old IBM machine that's running a suitable version of the operating system that can correctly download and run the .exe files that are needed to interpret the images that are on the CD-ROMs. And so you can think about this problem in longer term settings. I mean, imagine that here it is 2020, you collect a whole bunch of data, you store it in the cloud somewhere. And 100 years from now, if you're thinking, this data might be useful in 100 years, where will it have gone during that 100-year period? Will the cloud system have survived? Will the data have been copied into new media over time? Will the software that's needed to correctly manipulate or interpret or render the data still be executable 100 years from now? And if it isn't going to be executable 100 years from now, what should I plan on doing over the course of that 100 years in order to make sure that the software continues to run? And you can be sure that not all software is going to be upgraded to operate on every operating system, invented between now and 100 years from now. And so if you're really paranoid about this, as I seem to be, you might decide that you should, in fact, design and build virtual machines that can emulate old hardware, that can run old operating systems and run old applications so that you can correctly interpret the data. And in fact, there has been some demonstration of this capability at Carnegie Mellon. There was a project called, ARPANET. There's some background noise coming from someone named Picardo. Could you please mute your microphone? So coming back to the Olive application, Mahadev Satyanarayanan at Carnegie Mellon developed this project and then implemented a number of emulators for older hardware, and then ran old operating systems, and then ran old applications to demonstrate the feasibility of creating these virtual machines. And for those of you who are actively using cloud-based systems today, I'm sure you're well aware that virtual machines are a common way of providing application services to customers these days, all the way up to and including the possibility of running an emulation of an older piece of hardware so you could run old software. So one has to think in terms of preservation anyway, not only in terms of preserving bits, but also correctly preserving the executability of software that might go with those bits. That's a non-trivial effort, I think. And I think it also will depend a great deal on whether it's possible to establish a business model that will allow that kind of preservation to be provided. Because if there isn't a way to pay for this continued maintenance of utility of the data and the software that goes with it, if you can't find a way to pay for that, then it may not in fact survive. And that's a very important issue for the scientific community, to make sure that this digital preservation is taken into account as projects are organized and funded and the data collected. There is, in addition to all of that headache, which I've tried to summarize here, another set of issues that should occupy people's concerns. Some data needs to be protected from access, or to put it another way, some data needs to be access controlled. You can think of a number of reasons for this. One of them might be privacy. If the data had medical information about a particular person, it might very well be the case that you don't want just anyone to get access to that information. And so you need to have some way of controlling access. And that raises another interesting question, which is, how do you strongly authenticate a party who proposes to get access to that data? How do you identify who should have access to the data? What identifiers, what identity can you express and then test in order to assure that the data is properly controlled, access to the data is properly controlled? This gets to be very complicated if what you are trying to do is to preserve data for long periods of time, because some people who will need access to the data haven't even been born yet. So you don't know how to refer to them, at least not by individual identifiers. So what is, now you need a descriptor to say under what circumstances certain parties should be permitted to have access to the data. Some of those data access controls might have time limits on it. So now you have to record in the metadata again, under what conditions is the data going to be broadly and openly available, and under what conditions does it still have to be access controlled? If you're as paranoid as I sometimes am about this access control question, then you're also going to be worried about collecting information about access to that has been given to the data. In other words, tracking records of some kind that can be audited. And so that suggests things like log files have to be accumulated, and not just accumulated, but actually evaluated and examined in order to determine whether or not a breach of the access rules has occurred. And although perhaps some of you are thinking this seems like a kind of a paranoid thing for the data science world, but I can assure you that access control for data is a big issue in many conditions, not simply the privacy of medical information, but if you have spent a substantial amount of money collecting data from an experiment and you would like to use that data in order to enhance your academic professional stature, or to make use of the data for commercialization purposes, you would want to make sure that parties who should not have access to the data are inhibited. And you certainly would want to know if someone unauthorized party did get access to the data, you'd want to know that as well. So you can see that the whole notion of organizing a data sharing regime has many, many complex parts to it. It's not simply a matter of capturing data, digitizing it, and storing it somewhere. Now this takes us to another space, which is if you have all the data and if you have legitimate access to it, then the question is, what can you do with it? And assuming that you have all the metadata that you need so that you understand what the data is, then the question will be, well, what tools do we have in order to make use of the data? How can we apply those tools? In some cases, where the data is going to be useful because it might be used to compare a simulation or emulation of something and the actual data that's collected. I mean, this is fundamental to science, where you have a theory of about how something will work. You make predictions about what certain experiments will produce in the way of data, and then you run the experiment and you compare the predictions with the data in order to determine whether or not the theory is strong enough to make the successful predictions. So having tools for analyzing data is very important. And one of them being, for example, in today's world, that data is often used to train machine learning systems, typically multi-layer neural networks, which have turned out to be enormously powerful to help us analyze large quantities of data and to discover certain correlations and patterns that are embedded in the data, which might not be very obvious. Let me give you a concrete example of one of the more exciting ways in which we use these tools. Some of you are well aware of a number of space-based and terrestrially based telescopes, which are being used to try to discover suns in our galaxy that have planetary systems, and then to try to assess something about the planets. How big are they? How far away from the sun are they? Can we analyze the spectra of the sunlight going through the atmosphere of a planet, if it has any atmosphere? Can we detect the presence of certain chemicals, whether it's just elements like oxygen and hydrogen or nitrogen, or in fact, more complex molecular compounds that might give evidence of life? Well, that kind of data is very obscure, and it's also sort of embedded in a broad range of other noisy signals that we will have received. And so finding and detecting the data is a non-trivial exercise. I got very excited for a colleague of mine at Google who was participating in the analysis of data that had been collected from one of the space telescopes. I think it was Kepler, but I don't hold me to that. Anyway, an enormous amount of data had been accumulated, and it had been analyzed using these machine learning methods. And so his curiosity bump itched, and he went off and did his own analysis of the data and discovered a planet that other people had not found. And so I can imagine this must have been enormously satisfying, partly because this thing was obscured in this massive amount of data, and his analysis was able to reveal a pattern of essentially a pattern that diminished the light coming from the sun as seen in our direction as the planet crossed in front of the sun. So this kind of analysis has allowed us to discover all kinds of things hidden in data that might otherwise not be very detectable. At the same time, we've also learned that these machine learning tools are fragile and brittle, in the sense that they will sometimes identify correlations that in fact are meaningless or are simply flat wrong. We have some very definite indications of bias arising in some of the machine learning systems because the training data is too narrow for the actual application of the machine learning system. So the data sources that the machine learning system will be analyzing are much broader in their origins and their sources than the training data. And if that's true, then the resulting system will either fail to detect things that it should, or it will misrepresent or mislabel things that it does think it has detected. It's not so easy to discover that the training data is brittle or biased, because you have to have a model or a theory of bias before you can detect it. And so this raises a number of questions about our increasing reliance on these machine learning tools, which have been very spectacular in their successful detection and analysis of data, but which at the same time have also failed in fairly spectacular ways as a consequence of having inadequate training of the machine learning system. So I think that when it comes to data analysis tools, another thing that we have to be thoughtful about is the design and implementation and testing and validation of those tools against the data sets that they will be running against. So once again, part of the data analytics world needs to include the disciplines that are required for evaluating some of the utility and accuracy of the tools that we are using to make sure that the data is useful. So I hope I've been able to paint a fairly broad picture for you of the range of issues arising as we think about sharing of data, especially widely and over long periods of time. And I'm pretty sure I have not touched on every possible issue arising, but I'm hoping that during the Q&A period, you'll be able to identify other things that we should be keeping in mind as we think about the sharing of data among a broad range of scientists. Now, I want to spend just a moment on a non-scientific point here, because data gets used for a wide range of different purposes. And many times the data is used in order to establish policy. And again, one can be quite worried about the possibility that poor quality analysis will lead to bad policy, because the policy assumes, if the policy assumes that it is based on the data and the indications that data suggests the policy should take into account. So, so one of the things that I worry a lot about is whether or not the policy apparatus is drawing on the correct kinds of data and the correct kinds of analytical tools that justify their use in the formation and establishment of policy. So now we have yet another problem as data scientists to be concerned about, and that is what data and what analyses are we presenting to policymakers, and how do we help them correctly interpret the results? I'll give you a kind of made up example of something which I find very disturbing when people are using some kind of metrics to evaluate a proposal. If any of you are in the research community and you've submitted proposals to scientific research supporting institutions, and you hope that your proposal will be accepted and considered to be worthy of receiving support, then you probably have all participated in evaluation committees at one time or another, where you've tried to establish a set of criteria for evaluating a research proposal, and maybe you've even given numeric scores to the various criteria. Well, then the question will be, well, if you have a dozen criteria and each one of those has a score from 1 to 10, how do you combine, or should you combine, those various numbers in order to give a kind of figure of merit for the proposal? And it is enormously tempting when you're working with a number of proposals or trying to sort of winnow them down to a smaller number, to apply some formula, some weighting factor to the metrics of the various criteria and then come up with a number, which represents the quality of this particular proposal. The tyranny of numbers, I consider to be a serious potential hazard and one that we should be thoughtful about. You don't necessarily know whether the formula that you happen to have picked, what if it's some simple-minded thing like sum all the values and divide by the number of different criteria and get an average, and that somehow represents the proposal. Those are very simple-minded kinds of metrics. And if you allow yourself to be persuaded that these kinds of summarizing methods are legitimate and accurately convey the weight, so to speak, of a proposal, or something else that, you know, that in a contest, then you will have done great disservice, most likely, to the people who have submitted the proposal. So once again, these kinds of analyses should not be allowed to dictate results. They should be intended to help inform, but I think real human evaluations are quite important. Now, I will mention one other thing, which a very dear friend of mine has been exploring for the last couple of years, and that's the ability to compare policies by assigning values to different criteria that the policies are trying to articulate. And the purpose here is not to say this policy is better than that one, but in this particular case, the idea was to figure out whether the policies are in conflict or whether they are compatible with each other, or whether one policy contains another policy. If you're familiar with policy documents, you know that they typically are written in turgid text, and they can be quite difficult to figure out, especially if you have many clauses in the policy and some things that say, you know, this is not permitted, and under the following circumstances, something else is permitted. Reading the text of a policy and then trying to compare two policies is difficult. I'm sure you've encountered this when you've used online services that say, and here is our privacy policy, and then you have 30 pages of terms and conditions, and you're wondering, should I use this service or that service? And you have 40 pages of material from each of them, and you're trying to figure out which of the two or three or four is preferable. It's almost impossible. So finding analytic ways of representing policy so that you can compare them could turn out to be quite a powerful tool. And my colleague is not at Google, but elsewhere, has been exploring that possibility as well. And so here's a case where it's not so much a ranking system to decide something is better than something else, but rather to allow their compatibility or conflict to be detected using a fairly mechanical process. That only works for certain kinds of policy, for certain kinds of value metrics, certain kinds of descriptors of the policy. Perhaps it is necessary that there be a strict hierarchy of policy constraints for a particular issue. For example, it's wide open, or it's firmly access controlled. Only strongly authenticated parties can get access. You could imagine those being two of a series of possible access control policies. The wide open one being containing everything else, and the fully access controlled one excluding wide open access. So that's another kind of tool that we might imagine applying in our use of data sharing and data analysis. So, Mr. Chairman, I think I should stop there, and I've rattled on for a little past a half an hour now. And I would be very happy to engage in discussion and conversation if the participants have questions that they would like to ask. I can tell you that I have access to the chat room if that's a good place for the questions to show up.
Thank you, Dr. Vint. Thank you so much for sharing. You have covered almost all the aspects, right from data preservation to data security to data privacy to say how ML models will be using the data to come deciding the policy based on the data. I think you have got wide spectrum of the stuff. Now we are receiving a lot of questions. I will be taking some of the questions and I will be putting in front of you. And I have also some of the questions for you. Now, I would like to start with you, sir. What actually motivated you way back then in 80s to work on internet? Now internet has become like we think that we are born with internet, at least this generation. What was the motivation way back then?
So first of all, although my title, academic title is PhD in computer science, so I could claim to be a scientist. The real fact is that I'm more like an engineer because I like problems and I like to solve problems. I would also like the solutions to the problems to be useful. And of course, I would be happy if other people made use of the solution. So, I mean, most engineers, I think, are like that. They want to solve problems and they'd like to know that people appreciate and use their solutions. So internet was not something that Bob Kahn and I just woke up one morning and said, you know, why don't we invent this thing? It was actually motivated by a Defense Department problem. He and I and a number of others worked on an experimental network called ARPANET, which was named after the Defense Advanced Research Projects Agency. And it was an attempt to design and build a packet switching system that could link heterogeneous computers with different operating systems and different hardware, different word sizes and a variety of other variations into a common network. And the purpose for that was to allow a dozen universities to share information on computer science and artificial intelligence. So this is way back in the mid to late 1960s. And Steve Crocker and Bob Kahn and I and many others worked on that system. After the successful demonstration of the packet switching technology on the ARPANET, which was a dedicated telephone wire system. Now, we had dedicated circuits linking the packet switches together to form the ARPANET, and then we connected computers to the packet switches. That was so successful, and it was used heavily by the research community that was funded by DARPA, that when Bob Kahn got to the Defense Advanced Research Projects Agency, he started to explore the possibility of using computers in military command and control. Now, the implication of this is that if you had a computer and you could use it to manage the resources at your command, that the computer might be able to help you use those resources better than an opponent. And that could give you what we will call a force multiplier. If you had a smaller force, but you managed it better than the other guy, then your smaller force could overcome the bigger one. So this is all about information sharing. It's about logistics. It's about planning. It's about decision support systems. And so Bob, in conceiving of this possibility, realized that the computers would end up in ships at sea, airplanes, and mobile vehicles. And we had only demonstrated that we could hook computers together in air-conditioned rooms that didn't get up and move around. So he started working, Bob Kahn started working on a mobile packet radio system and a packet satellite system for long-distance communication, ship to ship and ship to shore. And so began designing and building networks of this type, mobile radio networks, packet satellite net, in addition to the ARPANET. And incidentally, this is around 1973, the Xerox Palo Alto Research Center, which was not very far from my laboratory at Stanford, was doing the Ethernet design. Bob Metcalf and David Boggs were doing that at a 3.3 megabit per second rate, which was dramatic compared to the modems of the day. So, so the problem that Bob confronted the two of us with was, how do we design and build a system that would allow an arbitrary number of packet switch networks to be interconnected in such a way that you wouldn't, that the host computers, the ones that were using the network to communicate, did not have to know how many networks there were, what the path was among, between the networks. How could they make sure that the data that went in came out the other side without any change or modification? That was the end-to-end principle. So his question was, how do we do that? And that was the engineering problem that we worked on way, way back in 1973, and came up with a design around fall of 1973, and published a paper the subsequent May of 74 describing what the internet could look like. So this was actually a technical engineering challenge, as opposed to a discovery or a sort of a, this didn't just form like Venus, being born out of the ocean. But then many, many technical issues arose. Lots of people were drawn into this whole design process. I ended up at ARPA myself, running the program for 6 years until I went on to the private sector in the late 1982. So this was a problem that needed solution. And the two things that I would draw from this history is that engineering problems are best solved if you have lots of people looking at the problem and thinking about solutions and evaluating them. And by good fortune, many, many people decided this was a very interesting problem. They wanted to participate. And the philosophy behind the research program was openness. The architecture was open so that people could add new protocols if they had new functions that the old ones couldn't support, or we could sweep in new telecommunications technology like optical fiber, free space lasers, and things of that sort. So the architecture was open, it was layered, and so you could change things inside of a layer without it affecting the interfaces on either side. So this was frankly, a spectacular exercise in freedom to design and to explore new functionality, to invite anyone who was interested to contribute. And I still think that's one of the strengths of the internet of 2020, that it still is evolving, new ideas are coming, new protocols. TCP/IP could be replaced by the QUIC protocol running over UDP, for example, and it has some nice features that TCP does not have. And of course, what we're doing right now is dependent on real-time communications across the global network. And so all of that has evolved over the course of the last 35 or 40 years.
Thank you so much for enlightening with us with the history. This younger generation may not be aware about this history, how this whole internet started, but your contribution has completely changed humanity, the way humans are today interacting, and perhaps this virtual conference, this virtual interaction with you is just the work you have done in 70s. In fact, that time even I was not born. In 73, I was just born, and that has laid down this whole foundation for internet. Another things are now this internet has proliferated over the whole planet. 5 billion people, they access internet, and even in India, like over 550 million Indians are using internet over their mobile phone. Now, I come across very interesting work which you were involved in, that is interplanetary internet, right? Would you like to really enlighten us and the audience that what is this concept? Elon Musk is working on sending the rockets, and you're trying to really work on connections on interplanetary stuff.
Well, first, thank you for asking. It's a topic I care a great deal about. I've spent the last 22 years of my life working on this with my colleagues. First of all, this is not intended to communicate with aliens. That was not the driving factor. Now, this one, however, was closer to the kind of the aha, why don't we try this, as opposed to the here's a problem, figure out how to solve it. Of course, there were problems, absolutely, that needed solution. So around 1997, the Americans were able to land a rover on Mars for the first time in 20 years. We had landed the Vikings, Viking 1 and 2 in 1976. After that, nothing worked for anybody. Things never made it. They crashed, or they missed the planet, or the rocket blew up. And so we had 20 years of unsuccessful attempts to get back to Mars. And in 97, the Pathfinder robot showed up. And this ignited a discussion at the Jet Propulsion Laboratory near Caltech in Pasadena, California, where I happened to have an appointment as a visiting scientist. So the team there and I got together and said, well, we're back on Mars. This is exciting. What would happen if we had a network like the internet, but which spanned the entire solar system? Of course, the first question is, why would you do that? And one answer is that it would give you more resilience and more richness of communication than point-to-point radio links, which is all we had ever had for doing space exploration. So the question was, could we build an interplanetary scale network? And we started out thinking we could use TCP/IP for this. And after we did a little bit of calculation, we realized that that wasn't going to work. There were two major problems. The first major problem is that the speed of light is too slow. It's only 300,000 kilometers a second. And the distances between the planets are literally astronomical. So even when Earth and Mars are closest together in their respective orbits, they're 35 million miles apart, which means it takes about 3.5 minutes for a signal to go from Earth to Mars at the speed of light, and of course another 3.5 minutes to get back. But that's when we're closest together in our orbits. But Mars takes 2 years to get around the sun. We take 1 year. And so the distances between Earth and Mars vary over the course of 2 years. And when we're farthest apart, it's 235 million miles. That's 20 minutes of transmission time, of propagation time, and of course another 20 minutes to get back. I can tell you that the TCP flow control protocols were not designed to deal with a 40-minute round trip time. So that's the first problem. The second problem is that the planets are rotating and we don't know how to stop that. So when you're communicating with something on the surface of the planet, as the planet rotates, at some point you can't talk to it anymore until it comes all the way around again. Or maybe you're trying to talk to a satellite and it goes behind the planet. You can't talk to it anymore. So the regime of operation, unlike the terrestrial internet, is variable delay, and very long and variable delay, and disruption. It's normal. That's the norm, as opposed to disruption being an unusual case. So we said, okay, we now understand we have to design a new suite of protocols, which we did. And we called those protocols the bundle protocols, because bundle kind of sounds like packet, and we wanted it to be similar. We have, so we had started writing prototype software and designing the protocols to overcome these challenges. And in 2004, in January, you may remember that 2 Mars landers arrived, Spirit and Opportunity, 2 successful additional arrivals on the surface of Mars. And they were intended to transmit data back on a point-to-point link from the surface of Mars back to Earth. Now, Earth has 3 what we call a deep space network ground stations in 3 places on the planet: Goldstone, California, Madrid, Spain, and Canberra, Australia. These are big 70-meter dishes, like honking big antennas, because the signal levels that you get from Mars are, very, very low. So the plan was to just transmit data back from the surface of Mars back to the deep space net on a point-to-point link. And the radios overheated. And of course, this created all kinds of alarm, because they could either wreck themselves, in which case no data would come back, or they could wreck other instruments that are on board. So they said, oh, we have to back off the duty cycle to keep it from overheating. the data rate that was available from the surface of Mars back to the deep space net was only 28 kilobits a second. Of course, the scientists were very grumpy about that, and they were even more grumpy when we said we'd have to back off on the duty cycle. So somebody noticed that there was an X-band radio on the rovers and an X-band radio on the orbiters that had been sent to Mars to map the surface of Mars before the rovers got there. So we took our prototype interplanetary software and we uploaded it to the orbiters and the rovers. And we've been literally running the prototype software since 2004. So we're talking 16 years now. Subsequent missions have used that prototype interplanetary software. In the meantime, here on Earth, we have been refining the protocol design and standardizing it with the Consultative Committee on Space Data Systems. And so all the spacefaring nations, including India, are part of the Consultative Committee on Space Data Systems, and they are now standardizing the interplanetary protocols. Those protocols are on the International Space Station. The most recent standard protocols are being tested on the Interplanetary Space Station. We've done some Earth to Moon tests as well on laser links at 600 megabits a second. We're very excited about this because laser communication could give us higher data rates than the lower rate radio communication. Finally, you are all aware of the Artemis return to the moon program that the US is now engaged in with hope to return to the moon in 2024. The interplanetary protocols are intended to be used for that mission as well. So I can tell you that we're very, very excited, the whole team, by the possibility that our work over the past 20 years will contribute over the next several decades to the expansion of an interplanetary backbone network.
Thank you, sir, for enlightening us with such a breakthrough research, interplanetary internet connection. And those who do not know, Dr. Vint has initiated the project of actually sending emails over internet when he was in MCI. And so today what we really see as our birthright, that we are able to really send emails over Gmail or everybody, everywhere. This was not the notion way back then in 84, sir, if I'm right. Yeah. So what was your motivation? What actually led you to start this project? What actually came into your mind? What was the problem way back then that you should send emailers over internet?
Well, and actually the original network design was not internet. Let me do two things here. The original concept for electronic mail arose during the ARPANET period,
right?
Using the predecessor to the TCP IP protocols called NCP over the ARPANET. One of the engineers at Bolt, Beranek, and Newman, the company that built the packet switches of the ARPANET, came up with the idea that since we had a file transfer capability, we could move email from one computer to another computer. And in order to do that, you needed to say which computer were you sending the mail to, and you needed to say who was it for when you got to the machine where the mail was supposed to land. And he needed to separate the user from the machine name, the name of the user from the name of the machine that the user's mail was on. And he needed to separate those two strings, and he looked on the keyboard to find a character which was not already used by all the other operating systems, and he found the @ sign. And so user at host was the formulation. So that was Ray Tomlinson from Bolt, Beranek, and Newman in 1971. I left ARPA in 1982, so a decade later, and at the request of a company called MCI that said they wanted to build a digital post office. So this is another one of those, I'm an engineer, they say they have a problem, go figure out how to solve the problem. And the solution to the digital post office problem was called MCI Mail. So it was a commercial email service. It was by no means the first commercial service, but it was the first commercial service to be connected to the internet, which is a whole other story, which I'll just touch on briefly, the internet was not allowed to be used by the general public until 1989. So think about it. We start way back in 1969 with the ARPANET and the internet in 73. So 20 years go by before anyone in the general public gets to use this thing. And it occurred to me around 1988 that unless we built an economic engine underneath the internet to support it, it would never make it into the hands of the general public. And so the government said, well, we won't allow any commercial traffic on the government-sponsored backbones. And I tried to break that rule by saying, can I connect the commercial MCI mail system to the government backbone internet? And at that point in the US, that was ARPANET, the ESNet from the Department of Energy, NASA Science Internet, and the NSFNet backbone. So I got permission to do that. And as soon as we demonstrated that we could interconnect commercial email services to other people on the internet, then the other commercial email services wanted to get connected to the internet as well, which they did. And in 1989, 3 commercial internet services popped up. So the side effect of trying to connect commercial email to the internet opened up the internet to commercial potential. And by good fortune, the then Vice President of the United States, Al Gore, helped to facilitate legislation that made it legal for all of this commercial traffic to flow on the government-sponsored backbones of the internet in the US. So all of this just shows you that if you sometimes you need to get legislators to do something in order to enable other things to happen, even if they're technically feasible.
And I think that led to this whole internet, email, and this privatization of internet actually led to Google, led to Amazon or eBay. And in fact, post 2000, all these models of machine learning and deep learning and data science just evolved on the top of internet. Sir, I would like to borrow additional 15 minutes from you. There are a lot of questions, if you give us permission.
I have another call that I need to get on. I can do about another 10 minutes, but let me just mention one other very important thing. After the 1989 beginnings of commercialization, another thing happened, and that was Sir Tim Berners-Lee's invention of the World Wide Web. And he released it in December of 1991. I don't think too many people noticed when that happened, but a couple of years later, 2 engineers at the National Center for Supercomputer Applications at the University of Illinois in Champaign-Urbana released a graphical version of a browser called Mosaic. And Jim Clark, the guy who started Silicon Graphics, saw that, got very excited about it, and brought Mark Andreessen and Eric Bina and others from NCSA to the US West Coast and started a company called Netscape Communications to build commercial browser and web server software. And they started that company in 1994. And in 1995, the company went public with an extremely successful IPO, initial public offering. And of course, that got everyone's attention, and lots of companies were started during this dot boom period. And then in April of 2000, there's sort of a dot bust because a lot of the companies didn't have good business models, and so they ran out of money and they collapsed. But the internet continues to grow, and of course it's growing in part because of all the applications that the World Wide Web has permitted to be built. And then in 2007, the iPhone came along, the smartphone from Apple, and that created yet another explosion of access to the internet, because you could get to the internet anywhere you could find a base station. And the mobile phone, of course, then had access to everything that was available on the web. And so these 2 technologies were mutually reinforcing. Okay, so I know you have questions, so let's go for another 10 minutes.
So,
And then
sir, we have, as we have scheduled to award a scholarship to 20 students, Aegis Graham Bell Talent Scholarship. So hopefully we should finish in 5 minutes, and then I'll take 2 questions from you in next 5 minutes. So
okay.
I am sharing my screen, and we take this opportunity, your presence, to declare the award for these students. I'll be should be able to finish in 2 minutes,
I can
3
see
to
that.
4
Yes.
time. Yeah. So this Aegis Graham Bell Awards, we started way back in 2010, sir. And this is to basically recognize innovators across the world, mainly from India. And innovators from large companies, startup companies, professors, they all participate from last 10 years. And we don't differentiate between startups and large companies. And we give them an award based on what innovation they have done. Under this award, we have also initiated National Talent Hunt. And this National Talent Hunt, the objective of National Talent Hunt, to essentially identify the potential leaders, those who can be leader in tech, primarily in exponential technology, be it artificial intelligence, data science, machine learning, deep learning, cyber security, blockchain. These are the areas. And what these students, they typically get, these students, they get 100% scholarship to study postgraduate program in data science, business analytics, and big data in association with IBM. They also have an option to study postgraduate program in applied AI, applied machine learning, deep learning, again in association with IBM. And the third program, which is a very important program, cyber security. And we cover most of the issues we have raised, which is like a data protection, data privacy, algorithms, and we have introduced a lot of AI and ML component in this program. The first phase, we gave award to 20 students, and the first award was in February in New Delhi, and our Honorable Minister Nitin Gadkari ji gave award along with the AICT chairman to 20 students. They got 100% scholarship, and out of these 20 students, 8 students were the girl student. We didn't do it by design. This came as by default. Now, the second phase award we'll be announcing in the next 30 seconds, sir, in your presence. And these are the students, and I will just read their name. Balaji T, Akhil Gupta, kindly activate your video. Silver Raja Deepak, Aman Gupta, Khushi Das, Manohar Singh, Nihar Shah, Opilapam, Pavitran, Priyadarshini, Ramaya, Sadhana, Sandhya Nayak, Sanket, Shivani, Shreya, Sumaya, Savitri, Vaishali, and Himanshu. So these are the 20 students, sir. These students were picked up through, say, All India examination. So thousands of students, they have applied. Then the online examination was conducted since the lockdown is there for last 2 months. And they have gone through the rigorous interview process. Some of them, they have done extremely good project on deep learning, machine learning, these areas. So congratulations to all of the winners, sir. That if you can really say some few words of wisdom to these students.
Well, I am very impressed with this whole program. It's very clear that all of you who are honored today worked very hard to get to where you are. And that's important because it's evidence that you're capable of doing that kind of work. That means that wherever you end up to go to work, they're getting the benefit of a great deal of talent and energy and creativity that you've already demonstrated, which is a terrific way to start your careers. So congratulations to every single one of you. I'm sure we're going to be reading about you in the headlines as time goes on with some of the ideas that you'll tell us and surprise us with.
Thank you so much, sir, for your motivational words for these future tech leaders. Now there are a couple of questions. So congratulations to all of you, and give a big clap to
Congratulations.
these students. And you can see, sir, out of these 20 students, 10 students are girly students and 10 students are boys. And this is again not by design. It has happened by default. And in afternoon, there was panel which was going on, say, women in data science and AI. And at last I jumped in, though I was not moderator, and I jumped in, I said, you don't have to design it. It is happening by design. It's happening by default. So the woman is getting more and more representation in this. Thank you so much, sir. I have a couple of questions which a lot of people are asking, and I also have in my mind. Uh, Gavin, why don't you activate your video? Dr. Gangopadhyay, Dr. Kulkarni, kindly activate your video. I have a couple of questions in my mind, sir, and a lot of people are asking. What will be the internet looks like in next 100 years, next 50 years? And how this internet, new era of internet is going to influence AI and data science and these cybersecurity exponential research, so that these future leaders, not only those who got the award, those who did not get the award, and all the participants, a lot of academicians, vice chancellors, professors are attending, they will get a future motivation, a direction where we should work. And also at Aegis, we can really lead research on those areas.
Well, making any predictions for 50 years from now or 100 years from now seems pretty hard, especially if you look back 50 years and ask, could we have predicted what we see today? I think there are several features of whatever the internet is 50 years from now that will still be there. I think it has benefited enormously from the openness of its architecture. So however it evolves, I think openness will still be very important. Layering will still be very important. Radio-based communications will be just as important then, 50 years from now, as it is now. We will have moved up into much higher frequencies. Base stations will have gotten closer together. We will probably be making use of free space lasers in addition to optical fiber. Fiber is still by far the most capacious of the underlying transport technologies. There's a report recently from a research lab that demonstrated a 40 terabit per second optical fiber system using 1024 QAM on a single channel. And so, I mean, it's just an enormous amount of capacity. And now if you have multiple fibers, you can just do the math and realize how much capacity there still is to be extracted from fiber-based things. Costs will come down. You can already see that. If you look at undersea cables right now, you'll see a proliferation of undersea cable technology. Companies like Google are starting to build their own cables because they're affordable. More so than before. Before you had to have a consortium of people. I think that internet-based devices will be everywhere. They'll be embedded in homes. They'll be embedded in our bodies, or at least they'll be carried by us. We're seeing that already. The Internet of Things is already starting to happen. We even have an example of what's going on as a result of the pandemic. Right now, there are doctors who are saying, please don't come into the office. We don't want to catch the COVID-19 disease. Let's have a consultation remotely, as we are doing right now. And of course, my reaction to this is, what kind of medicine is that? You didn't take my temperature and my blood pressure and my pulse rate and everything else. So, you know, what kind of medicine can you practice? And of course, one of the answers is, well, we need remote sensors. And so I think the Internet of Medical Things will almost certainly have evolved dramatically over a 50-year period. The idea of remote consultation, capture of the physiology of a person will become much more normal. And of course, we'll be gathering genetic information and all of that entails, including the biome in the gut, which plays such a powerful role in our immune system. So there's a whole lot of stuff going on there. I think just looking at the computational side of things, everyone here keeps hearing computational X, computational biology, computational cosmology, computational linguistics. and even computation in aid of the humanities and arts. And so 50 years from now, I think computing will not be thought of in some special way. Computation will be normal. All kinds of devices will have both computing and communications capability. We won't even think about it. Of course, these devices around the house are able to use the net, and it will be either wireless or wired or both. So I think we may still call it the internet, even if the implementation is dramatically changed over time. But the idea that we will casually assume communications is possible will be there. Now, machine learning has also taught us that we can make these systems more convenient to interact with, whether that's speech communication or diagrams or something else. And we're also starting to see great success in translation. So I think that we could easily have this conversation maybe 10 years from now, not having to wait 50 years from now, where each of us gets to choose whichever our preferred language is, and the system will translate back and forth from the speaker's language to the recipient's preferred language. And I think we will get to the point where it's actually pretty reliable. We're not very far away from that today, at least in some languages. So it will be ubiquitous, it will be high speed, and it will be implemented in almost any device that's capable of holding a piece of computing.
Thank you, sir. Thank you so much for giving us the direction and future. And this spoken web research I have seen in IBM way back, and now we are seeing a lot of conversational AI. So what you're saying that internet led on say medical stuff, we should be able to really just talk whichever the language we want to really have, and these barriers of the language, the barriers which is led by say access to the information, and I call it the birth penalty. And I think your research has really gave us a path, a direction wherein we can really remove this birth penalty by giving access to the right kind of information at affordable price, and not only the information but the education and the knowledge. And currently in India there are like close to 370 million students. They are not able to attend the classes, and which is bigger, 20 million more than the America's population. And this internet is actually powering them to attend classes sitting from home. And in fact, we have another company, MUni, and we have conducted, now we are conducting examinations across the country online, where AI is empowering, taking the photographs and videos. And thanks to all the innovation you have done, sir, this power of internet which you have given, and that has really powered the whole humanity. And I express my sincere thanks and gratitude on the behalf of Aegis, our partner AICT, our partner FICCI, MUni campus, all the delegates, and the whole India, and perfects the whole the humanity. Thank you so much, sir. Thank you so much for being with us. And hopefully next time we'll take much more time of you, and we have hundreds and hundreds of questions which we could not really cater during because of this time limitation.
Well, I am sorry that I had only a finite amount of time. I really enjoyed the chance to share some of these ideas.
You gave 13. You gave extra 13 minutes, sir. so great of you. Thank you, sir. Thank you so much. We are honored to have you.
Thank you for allowing me to join you today.
And I take this forum to congratulate Gavin, Ritin, Nimit. Gavin has worked day and night to really make this success. Gavin, congratulations, all the team, all the participants. Thank you, sir. Thank you so much.
Thank you. Bye-bye for now. See you on the net.
Yes, sir. Okay. Bye-bye, sir. So we come to the closer of this two-day conference of Data Science Congress. Thank you, guys. Thank you so much. And all the award winners, keep working, keep studying hard, right? And I know a lot of you have come from very humble background. So use this time to really study, and hopefully we will hope to really welcome you once this pandemic gets over in our campus in Mumbai and Bangalore. And even if things doesn't get settled down, the internet is there. But the way things are moving, hopefully this whole crisis will get over by September. Thank you. Good luck to you, and all the best wishes to you. Stay safe and stay healthy. Thank you so much, everybody. Bye-bye. Good night.